Hi everyone, I am Matin Ghavami. I'm a second-year PhD student at MIT, Vikash, advised by Vikash Mansinghka. And today I'll be presenting work with Mathieu and Martin Rinard. Our work is about exact inference. Exact inference is possible in a wide variety of models, like finite discrete models, linear Gaussian, state space models, sum product networks, and other example classes. And because of the wide applicability of these model classes, there's lots of different probabilistic programming language specializing on one of these classes and guaranteeing fast, exact inference in those. But the approaches of these languages are somewhat disjoint. And today in this talk, my aim is to show that because the set of queries that we want to evaluate under these languages are somewhat structured, we can unify them in this framework of sum product networks. Sum product networks are a simple way to model probability distributions. They rely on mixture distributions and product distributions, and as such, they have very nice analytical and computational properties. There's many equivalent ways to define a sum product network. In this talk, I just take a sum product network to be a weighted rooted tree. And in this tree, we have three types of nodes. Each node carries two categories of information. A denotation, which is a probability measure, and then a tuple of addresses, a tuple of strings associated with each node that we call addresses. And we associate the entire network with the addresses associated to its root and the denotation of its root, so that way we can interchangeably talk about a node and a subtree at that node. The first type of node in a sum product network is a leaf. It comes equipped with the address and the measure that it represents. The next type of node is sum nodes. They denote mixture distributions of their children, and the mixture weights are given by the weights on the edges from the sum node to the children. The sum node needs to have certain consistency conditions to be well defined. Specifically, the addresses of the children should all be the same, and at that point we associate with the sum node itself the same tuple of addresses. And then we have product nodes that denote product measures of their children. And we also need to have consistency conditions there, meaning that the addresses of the children should not intersect in any way. And then the address tuple associated with the product node itself will be the concatenation of those addresses. Our main character in the talk is, I don't know what that was, sum product inference interface, or SPINI, which is an interface that we require every node in the sum product network to satisfy. And it has 5 methods in an object-oriented kind of way of a method. And each method takes one argument. The first one is sample, and the argument it takes is just a seed. And what it generates is a sample from the network that it was called on. The next one is called PDF, for probability density function. What it takes is a partial assignment of values to the addresses that the network is associated with. And what it gives is the marginal density of the measure denoted by the network at the given point. Now, since we're talking about densities, the density needs to be defined as some base measure, and kind of the same way we associated address tuples with each node, we can associate base measures. There's some caveats there, we can talk about it later. The other method is called prob. This time, instead of a description of a point, it takes a description of an event and gives the probability of the event under the measure represented by the network. And the last 2 methods concern conditioning. Because conditioning on an event and on a random variable are kind of different mathematical operations, we have 2 methods, different methods implementing them. The first one is the condition method. Its input is similar to the PDF method, and the output is another network that is the first network condition at the values given in the input. Note that the address that we condition on is removed in the output network here, so there's no address A. It's conditioned out. The other method is called constrain, and the input is similar to the prob method, so it takes a description of an event, and it outputs another network that is the original network now conditioned on this event. And this time the addresses didn't go away, but note that the distribution at some of the leaves changed. So it went from a normal to a half normal distribution. Okay, the nice thing about sum product networks is that they have this property that if the children of a node satisfy the SPINI interface, the node itself will satisfy the SPINI interface. And this is because conditioning, sampling, density evaluation, etc., in a mixture and a product kind of reduces to the corresponding operation on the mixture components or the product factors. And so this allows us to see that by induction, if the leaf nodes of some product network satisfy this interface, the entire tree will satisfy the interface. And since these methods are kind of reasonable things to want from a language supporting exact inference to implement, this is how we can see that we can unify exact inference in the framework of some product networks using this interface. Now, what's an example class of some set of distributions that satisfies this interface? Well, Gaussians are kind of nice. We know how to sample from them from multivariate Gaussians. They have nice densities, and they have kind of nice closure under conditioning properties that are used, for instance, in Gaussian process modeling and things like that. It's a little bit more complicated when you want to constrain a Gaussian random variable to take values in a certain set. If we let that set just be a polytope, meaning the feasible set of linear inequalities, then there's a large, those random variables are now called just truncated multivariate Gaussians, and there's a large literature on how to efficiently sample for them and evaluate their densities and probabilities. And so we have a lot to leverage, basically, to implement the spinny methods for this class. Another class is distributions on the line if you have access to their CDFs. And so, for instance, if you have access to a CDF and its inverse, we can use the inverse transform technique to generate samples. If we can use automatic differentiation, we can get the PDF by differentiating the CDF, and we can scale and kind of shift the CDF to get the CDF of like a constrained version of the distribution, or if we want to get the probability of an interval, we can just subtract the CDFs at the endpoints. Because of the nice kind of independent structure also encoded in some product network, if you want to condition on a single random variable, it turns out that either the random variable gets removed from the tree or it stays unaffected in the tree. And actually, this class of distributions, leaf distributions for an SPN, is the class of distributions that the popular probabilistic programming language SPPL uses. So in that sense, our approach can be kind of viewed as extending SPPL with like multivariate leaf nodes. But the good thing is then, because we have like these larger class of leaf nodes, languages that rely on this kind of representation can support algorithms that SPPL can't, for instance, linear regression or Kalman filtering in linear Gaussian state space models. All that said, we have some limitations also compared to SPPL, things that we haven't discussed here. A main part of SPPL is a modeling DSLs, which has these high-level primitives that the users can use to like specify models for, and then the model gets compiled down to like the sum product representation. And if we want to have a modeling DSL for our sort of representation, we need to add additional syntax and like enrich the type system. Similarly, SPPL supports like a wide variety of transformations that you can apply on the leaf nodes. And that's because CDFs of push forwards have like kind of nice analytic formulas that we can use. Definitely, we don't have nice analytic formulas for any distribution satisfying the spinny. So we need to be careful about what sort of push forwards we can support on what random variables. Lastly, to be a practical language, and to be able to be used on real-world data, SPPL does a lot of performance optimizations on the sum product networks that it generates. And if you want to have the same sort of performance optimization, so we can have a high-performance language, we need to make some modifications. In particular, we need to like specify rules, specific rules for the new types of leaf nodes that we add, and we need to also go inspect the parameters, not just the types of these things. So in summary, some product networks are kind of cool. They might allow us to unify exact inference using the spinny interface. And these are, I cited a bunch of papers. These are all the ones if people are interested. And I'd be very excited to speak more with you about this during the rest of the workshop. Thank you.